All right, everybody, welcome back. We're going to go over some more Physics 2 content, looking at circuits, electric circuits. So let's jump right in. I'm going to pull up one of these questions. Bear with me. I think I'm going to go through a few more than I did last time. We're going to see a lot of the similar content coming up. This question is, no capacitors in here. I'm going to show you, here's a picture of the circuit. And they're asking us, a student connects a circuit shown above and plans to make measurements to determine how changing the resistance of a variable resistor affects the current through the battery. Okay? The resistance of resistors 1 and 2 are known, but the possible range of variable resistor is unknown. The student only has a voltmeter, as shown. Will measurements taken with the voltmeter allow the student to determine the current in the variable resistor? Why or why not? Okay. So they're asking, will this measurement, this voltage, right? So it's voltage across here. Sometimes we would call this maybe V1, right? Will that allow us to determine the current in the variable resistor? So would we be able to figure out what I over here is? That's the question. If we know this, can we find this? So let's think about what we know about circuits and what we know about these complex circuits, right? We have some resistors that are in series, and we have also the series combination is parallel to this other resistor. So let's just ignore the voltmeter for a second and think about what's going to happen here. Okay. So we have some voltage, total voltage from the battery. They don't talk about that at all, so just leave it as V. Maybe I could even call it V total or V battery, whatever you want to call it. And that voltage is going to be driving this current, right? Current will leave the battery. We usually call this total current, right? IT, right? Or the battery's current. And then that current will split. Some of it will go here. I'll call it I2, even though it goes through resistor 2, that current. It also goes through your variable resistor, so this is I2 over here, right? And then it splits and it goes down here, I1. So what do we know? The total current is equal to I1 plus I2, okay? That makes sense. So if there was some way I could figure out the current here, if I was able to figure out the current here, then maybe I'd be able to figure out what this current is, if I also know the total current. All right. So what most think, you see this and you're saying, all right, I know R. I know the voltage here. So on this, I could use Ohm's law. V equals IR. I know R. I know V. I can find I1. So now I just need the I from your battery, your I total, and then I know I2. So how do we figure out I total? Well, we'd have to be able to figure out our V equals IR for the total circuit, right? So this could be voltage from the current from the battery, and I'll call this equivalent resistance. Problem is, we know only 2 of the resistors. So we won't be able to find our equivalent resistance, which means we can't find this, which means it doesn't look like we're going to be able to figure out I2. Now, let's just take that one step further. That's actually the complex way to think about this. There's an easier way to think about this problem. If we know the voltage from this battery, okay, I'm going to say 9 volts. I like to go with 9 volts, 9-volt batteries, but it could be any voltage. This side of our battery is a positive, right? okay? And everywhere along this circuit has that till you get to a resistor. So everywhere along here has the same potential as this side of our battery. In this case, we'll call it a positive 9 volts. Everywhere, positive 9, positive 9, positive 9. All the blue is positive 9. And if it's a 9-volt battery, the opposite side, we'd call that 0. It's ground or 0 volts. No more potential once we get to the back side of the battery. And everywhere in this wire, everywhere until we go through a resistor, everywhere has 0 volts potential. So what do you notice here? If you're measuring across this resistor, that voltage is always going to read whatever it is at the battery. You're never going to get a different, doesn't matter how much current is flowing this way, doesn't matter what this resistor does, always, always, always your voltmeter is going to read the same value, which means change this all you want, your meter doesn't change at all. So there's no way that this voltmeter's reading can tell you any information about the resistor. So that's it. Let's see another problem. All right, we'll take this one. I hope my colors don't bleed through too bad. I hope you could see that. All right. Oh, wrong spot. We'll do a different one. Sorry. There it is. Okay. Another circuit. Okay. In the circuit shown above, the switch S is open. The capacitor is uncharged. And the current through the battery is 0.5 amps. At what time is the current through the resistor in the middle branch 0.5 amps? Okay, so let's think about this for a moment. What do we know about capacitors? Okay, we know that they can only charge or uncharge. Once they're fully charged, no more current is flowing. So when we first close this switch, what happens? Well, let's think about before the switch is closed at all. We end up with current going around our circuit. It's a pretty simple circuit, actually. In that case, switch open, you just have two resistors. It would be a nice, simple problem. Then we close our switch. This whole side of the capacitor, this whole plate, has room for charges to flow. Okay? So current will flow into this branch now. And you get a charge separation on your capacitor, right? And the charges will build up until they're fully charged and current stops. I want to really make this clear. This gap inside the capacitor is actually a gap in the circuit. There's nothing connecting those two plates together. You could put it, it's not going to continuously flow across here, okay? Even with the dielectric, that dielectric is stopping the flow. So what happens is this plate can interact with this plate and create an electric field here that will set up this charge separation, but current will never flow across this gap. That's what happens when you put too much current through a capacitor and it pops, right? You burn out a capacitor. That means that there's been an electric spark that jumps across the gap. In all of our circuits, we're actually never going to be popping those capacitors, okay? We keep it simple, and these are all just regular old capacitors that are being used in their proper implementation, and they're going to be flowing. And you'll still have your plain old 2 resistor series circuit. Once that would be called what they call a steady state when it's fully charged. Okay, that makes sense. So let's go back. It's uncharged. We close the switch. Now current will flow into this branch. Okay, so current flows in. Then what? Charges up. Once it's charged a little bit, less current will flow into that branch. Charges more, less current, less current, less current, until it's fully charged, reaches Q. And then no more current. So, what are our choices? And I'm talking about the top, the same exact current's happening here on the bottom branch. Okay? So when that current starts flowing from here out. So our choices are immediately after the switch is closed. Well, we definitely know that there's going to be some current flowing there. Maybe you don't know if it's going to be what they're asking about. Maybe we don't know. Is it the 0.5 amps they're asking about here? Well, is it the 0.5 amps? Maybe I'm unsure, but I do know when it's immediately closed, current will be flowing. When the circuit has reached a steady state, no way. There is no current flowing. Only a wrong answer. Sometime between when the switch is closed and the steady state is reached. Maybe. At no time at all. Ooh, maybe. And it turns out you end up flow right when the switch is closed. What happens is all of the current, they see this empty space for charges to flow to, almost like all the current is allowed to flow here. Okay? All it goes in there, and then hey, I don't want to go there anymore. It's almost as if there's more resistance there, and then some will branch off here, and slowly it'll get back to its 5 as before. Okay? So, question 7, same circuit. Let's read what it says. In which position, open or closed, can the current be the same in the left and right branches? And I kind of brought this up already. When can the current be the same here, left branch, and here, right branch? Well, the only time it's going to be the same on both sides is when no current is flowing here. When does that happen? It happens when the switch is open, of course. Well, then that means the left and the whole top and the whole right and the whole bottom all have the same current. There's no junction rule. There's no splitting of that current. When this is closed, at the beginning, when it's first closed, these are not equal, right? Some of the current is flowing into the middle. Almost none is flowing over here. And slowly, more and more flows over here until no current is flowing in the middle again. And when no current is flowing in the middle again, that's when it's as if the switch was open. This charged capacitor is fully charged, we're in a steady state, and no current is flowing in the middle branch, which means we go back to our original situation. So it can happen that this current and this current are the same in both scenarios. In both, switch closed, as long as the capacitor is fully charged, and if I could pull one up. Okay. So this is one of the others that I wanted to see. Here we have a circuit, 2 identical resistors, an uncharged capacitor, and a switch are connected to a battery in the circuit shown above. The switch is open, and the circuit is allowed to reach a steady state. The switch is then closed, and the circuit again reaches a steady state. Which of the following correctly compares the potential difference and explain the comparison? Okay, so think about this. Switch is open. All right, well, if we first plug in our battery, what would happen? Current flow starts charging up the capacitor. Okay, that makes sense. Then the capacitor is fully charged. What did we say? This part of the circuit's completely out. What did we say when a capacitor is fully charged? This gap does not allow electrons to jump from the negative side to the positive side. They can't bridge that gap, which means once fully charged, R1 has no current at all. Now we close the switch. Okay, now what happens? So, are we closing the switch when this has reached steady state? Uh-oh. we got an alarm going off, which means we have no more current. Then the switch is then closed. So the capacitor is fully charged when we close our switch. Okay. Then what? Positive Q, negative Q on this side. We're fully charged. If we know anything about capacitance, remember that our capacitance equals Q over V. Okay? So, is this Q going to be different when the switch is closed? The capacitance is the same, right? It's labeled right on our capacitors. You can only change changing the physical properties of this capacitor. Take a capacitor and plug in a new capacitor, right? So we can't change C. If maybe there's some more Q going to go in here, or maybe less Q will fit in. So does V change when the switch is closed? This is just like our other problem before. There's a possibility. It's a little complex. Actually, we're not going to go through this. If this was not here, if this resistor was not here, you might think about it and say, hey, this is connected directly to my battery. This side's connected directly to my battery. My V is the same. In this case, things are a little more complex, right? And this resistor has some amount of current in it, which means it's using some voltage. So the voltage that gets to this side of this resistor is different than what's attached to my battery, right? It's a little less because this is using some of that voltage. Now, if we close this switch, our current of our whole system will change, right? V equals IR, our R equivalent with one resistor or two will be different. With a different resistance, we end up with different current, which means over here, this same resistor with different current through it will have a different potential difference across it. It will use up more voltage or less voltage from this battery, which means, yeah, V may change. So this Q may or may not, it may go up or down. Now we could do the calculation. I'm not going to go through that. If you'd like to think it through and understand, really, will this discharge a little bit or will it gain a little charge when the switch is closed? I think that's a really good exercise to think about. But we don't really have to worry about that because at some point it reaches steady state again. And that's what they tell us. We close the switch, it reaches steady state again. Now once it reaches steady state, now current can flow and it's just flowing around the outside. Steady state means this part of our circuit is no longer involved. Current's not going through there. It's fully charged, whatever that is, and now current is flowing around the outside. And it's flowing in R1 and R2. So I1 in situation 2 has some value. I'm just going to say it's not equal to 0. Okay. So what are they asking us about? They're not actually asking about the current. They're asking about the potential difference, the voltage drop across here, right? So they're actually asking the voltage drop across this resistor. Well, the potential across R1 is less after the switch is closed. Okay, so let's think about this. If we know that we have current in the second situation, but there's no current in the first situation. If there's no current flowing through there, what does that mean? It means that everywhere in this side, right, has all reached, this is situation 1. This is not involved. Everywhere in here has the same potential. So in situation 1, the voltage difference across resistor 1 is actually 0. Okay, so the potential across R1 is less after the switch is closed. It's not less. It's not less than 0. The potential across R1 is less after the switch is closed. Nope, it's not. The potential across R1 is greater after the switch is closed because before the switch is closed, there's no current in R1 And after the switch is closed, there is a current. So actually, I want to point this out because this is a really good test-taking strategy. If you didn't know the things that I was talking about and realizing, that there's no current at certain times and other times, they're actually, in their explanation, you would be able to read this, and if you really understood what it was saying, you might say, oh, I wasn't thinking about that. I forgot. Oh, yeah, there was no current flowing. Now there is. So this actually can give you information. The problem is those explanations and the wrong answers could be misleading you as well. But read through them all and read the explanations, and maybe one of them will jog your memory and make, oh yeah, now I remember that. Okay, that was helpful. And I know for a fact that's true, so that makes sense. Okay? And let's just read the last one just for consistency. Make sure that there wasn't some trick question in here. The potential across R1 is greater after the switch is closed. We said that. Because the total resistance of the circuit decreases. No, that's not a reason. And does the total resistance decrease? Well, these are in series, and no, that doesn't make sense. That's the wrong answer. All right, so I hope that helped. Just a couple of the electric circuit problems for you guys to take a look at. And let me know if you have any questions. You can put them in the chat or in the comments below, or reach out to me directly. And see you next time. Take care.